All right. Thank you very much to the organizer for inviting me. So I want to talk about some recent work that we had with Alberto Rosso, who was visiting recently, and people in my group, Jay, Ala, and Edan. Edan now is faculty in Amsterdam. So I want to tell you about flow in amorphous materials. Now I want to focus on particles that are actually soft, deformable. And I want to focus on the case where you don't have any temperature. So the kind of system I have in mind are a foam or an emulsion, for example. Let's say your mayonnaise. So what happens when you shear very slowly a mayonnaise? So the typical response would be like this. So you impose some strain. Let's say that initially you impose a strain very slowly. And you will have some transient response, which is very interesting, but that I won't talk about here. And after this transient response, you go to some asymptotic behavior. And the value of the applied stress here, I would call it sigma c, and I would refer to it as a yield stress. Now you can look at a similar curve if the shear rate is actually larger, gamma dot increases. And what you find is that then the plateau value, for many materials, the plateau value of the applied stress actually increases. But what's interesting is that it increases in a singular way, with some exponent called the Herschel-Berkeley law. So that has been known for some time. What has been realized more recently is what's going on that at the microscopic level, the dynamic is very rich. So what you can do, for example, numerically, is look at a finite size system, and you shear it adiabatically, and you look at the dynamics. And what you find is that you have periods where you load elastic energy, and you have periods where you actually release this elastic energy. And those release in energy are very broadly distributed. If you look in real space, so this is a map of the displacement for a big avalanche, you find that there is an interesting spatial organization of plasticity in those materials. So this map of displacement shows that you have some kind of slip lines there, but within those slip lines you have smaller slip lines orthogonal to it and so on. So you have this kind of fractal avalanche structures. So what I want to propose in this talk is to build a correspondence between this microscopic behavior and those macroscopic observations. And one theme that will be important is the connection between this yielding transition of soft amorphous solids and the depinning transition. So many of you in this room are very familiar with the problem of depinning, where you have some elastic manifold and you try to push it in some disordered medium, and it gets spin. And what you find is that if the force is too small, essentially it's going to stop. After a transient, it will stop moving. You need to go beyond a critical force to have motion of the line. If you look at the velocity versus force relationship, you find that it is singular above the critical threshold force. So that looks very much related to what I just described for amorphous solid. If the strain rate maps into the velocity and the shear stress, the yield stress maps into the critical force. At the microscopic level, it's also very similar in the sense that at the critical force or at the critical stress, as I told you, the dynamic is very jerky and consists of those avalanches. So those problems seem very similar, and in fact, it has been proposed in the literature that maybe they even fall in the same universality class, at least for some aspect of it. So here I want to argue that it's not the case, and that's related with a sort of curious behavior that you find in terms of finite size effect. So if you look at a system like this, you can consider at which rate you trigger plastic event or avalanches, let's say at forces below the critical force. And in the depinning problem, you find something very natural, which is that if you have a line that's twice longer, so if the system is twice larger, the rate at which you trigger avalanches is also twice larger. It turned out that for this problem, it's not the case. So if you look at a system that's twice bigger, than a smaller system, you find that the rate at which you trigger plasticity is not twice larger than what happens in the smaller system. So that's telling you that if you want, as you look at bigger and bigger system, effectively the system becomes more stable. Also telling you that this part of the system and this part of the system must talk to each other in some way. So the contention of this talk is that once you understand the microscopic reason for this effect and you include it, then the correspondence with the depending transition becomes very rich, and there are many ideas of the depending transition that you can just apply like this and maybe are going to work. So since my session is on jamming, I should also contrast this with the problem of the jamming transition. So as you heard this morning, there was a lot of work in the last 10 years considering purely repulsive particles interacting with some finite range. And as you heard this morning, a key parameter is the density or the packing fraction phi. If you're below some phi, you don't have a solid. But if you're above some critical packing fraction, then you have a solid, and it is a yield stress material. So what I'm interested in this talk is, say you look at a large phi, you're not close to jamming transition, and you try to understand how flow takes place when the strain rate, so I added an axis which is the strain rate, as the strain rate goes to 0. So as you approach this line, the dynamic starts to become singular. I want to emphasize that at best, everything I will say will only hold in the limit where the increase of applied stress is much smaller than the yield stress. You're really probing the solid in some sense. If the strain rate is too large, then you will enter in another regime. So if the stress is much larger than the yield stress, which is also interesting and that we're also studying, but which I think has very little relationship to this one. What's worrisome in some sense that many of the experiments that actually measure this Hershey-Berkeley exponent typically probe this crossover. So it would be really nice to have experiments that are only here or only here. So you have this sort of line of critical point corresponding to the yielding transition, and they end with one point which is the jamming transition. So you can extend this diagram and also look at what happens at smaller phi, right, as you heard this morning. And one region that is especially interesting in this diagram is this red arrow here. So you have a system of dilute, so you don't have a solid, so you have particles like this, and you shear them, but very slowly. So they are elastic particles, so when you shear them, there is some viscous stress, but if you shear very slowly, this stress is very small, and so the particles are essentially not deformed. So when you're at vanishing strain rate, essentially what you're describing is a suspension of hard particles. And a suspension of hard particles, if you're non-Brownian, and you can show, that's what my comment to Eric, that you can show that essentially the rheology here is going to be purely Newtonian. But it's still interesting. What you find is that, for example, the viscosity actually explodes as you approach the jamming transition. And you also have diverging length scale. So I can just illustrate this with a movie. That's a movie, 2D particles in a fluid. It's a very simple model. You change a bit the packing fraction. Here you're away from the jamming transition, and here you're just closer. What you see in black are the contact forces between particles. And what you can see just with the eye is that there is a sort of growing length scale. Here it seems to flow very smoothly, whereas here it seems like locally it's moving as a block. So if you were just looking at velocity correlation, you would see a growing length scale from those pictures. So in this, it's the same rate. The only difference is a slight difference of packing fraction. So here the system seems very different because from the yielding transition problem, because you're never loading elastic energy, right? It's purely geometry that seems to matter.
Is there a size dependence on this?
Yeah. So this is bigger. Those particles are bigger than those. No, so those are a small portion of bigger systems that have the same size. So in fact, the real system here would be a square.
Of course, you can expand the system.
Yeah. So that has, from much it has nothing to do with percolation. So the jamming transition is not percolation. You percolate and you have contact force spanning the system much before you reach the jamming. So it has to do with more rigidity percolation than percolation. All right, so why am I telling you all this? Although I think the physics is very different from the yielding transition, I think there are some ideas which we introduced to understand this system that are going to be useful for the yielding transition too. So the way we propose to think about flow near jamming of hard particles, and I think we made some recent progress last week, so it's on cold mat now, is essentially thinking about flow as a perturbation around the solid. So we think that configurations that you visit in flow are very similar to jammed configuration. So in jammed configuration, essentially particles are making enough contact to have enough constraint to forbid motion. Like jam configuration to which you give a kick. By kick, I mean an additional shear stress. So if you give an additional shear stress to this system, the force in the system are going to change, and some force are going to be negative, and those contacts are going to open. Those are those red crosses here. So those contacts are going to open, and then you can flow. And what you can show using geometry that flow properties like viscosity or velocity correlation will be governed by the number of contacts that you actually opened. It turned out that this number is not trivial, and it has to do with the fact that soft spots in the system, here I really mean weak contact, have a non-trivial density. So if you look, for example, at the distribution of contact forces in the system, it's actually controlled by a non-trivial exponent. This exponent, we argue, enters in the rheology near jamming. So I think this is going to be very different from the yielding transition, but I think there are two ideas that are going to apply to the yielding transition too. Is that the density of weak spot in some sense is singular, and that the exponent that characterizes density enters when you want to describe flow. And the second idea, which I don't have time to explain here, is that this exponent essentially has to do with the stability of packing. You can show that if it was just a bit smaller, the packing would be unstable. As soon as you touch it, it would completely rearrange.
What's the value of that exponent?
0.4. But I mean that's sort of orthogonal to my current talk. But so that the stability, if you want to understand the amount of soft spot in the system, thinking about stability is very important. So essentially, I want to use the similar arguments for this problem. Now, the sort of excitation soft spot in amorphous solids have been discussed for a while. They are called shear transformation. So for example, if you look at quasi-static shear and you try to look at what happens when, right at the beginning of an avalanche, what authors have found is that the beginning of an avalanche starts with a local rearrangement of a few particles, called a shear transformation, if you want. And this shear transformation corresponds to local strain, so it's going to generate some stress that propagates in the system, which in turn can trigger other shear transformation elsewhere in the system, and that's what makes those very nice patterns. They consist of many shear transformations. So the question I want to discuss is what is the density of this object? How to characterize it? Oops. Sorry, I will go this. Yes. So the way we think about it is in some sort of mesoscopic way, where you look at your system and you cut it into many boxes, much larger than the shear transformation size, the few particles that can rearrange. And in each of those boxes, we think about a parameter that describes this box that tells you the distance to a local instability. So if you want, xi would be the amount of additional shear stress you should apply on a box to make this box yield. Okay? It turns out that at the deepening transition, if you are doing the same, defining the same quantity, you could look at the distribution of all those x, of those local distance to threshold, and it would be boring. So it would, when x goes to 0, this would go to a constant. At the yielding transition, those authors, very nice papers, propose that actually this distribution was singular and would vanish when x goes to 0. So in this paper in particular, they argued that this exponent was governed by a local process and should take the value 1/2. So our contribution here is to say that theta is actually instead a non-trivial exponent, and that's really what governs it is the fact that you have long-range interaction between shear transformation. And we produce an argument to show that purely from stability reasons, P of x actually has to vanish when x goes to 0. So this is the argument, and this is pretty simple. So we think about triggering a shear transformation at the origin of the system, and we ask what happens next. So we know that there will be a response in stress, and it decays as a dipole because there is no monopole on force. So it decays at 1/r to the d. And it has some spatial structure that is not very important for me, but its sign varies. So in average, it's 0. So let's assume that you don't have any singularities, that P of x, when x goes to 0, is larger than 0. And let's trigger one of these guys and ask how many new shear transformations are going to yield in response to that. That's easily computed. So if you assume that P of x does not vanish, the probability to trigger something here will just be proportional to the amplitude of the kick over there. So to see the mean number of new triggerings that I create, I can just integrate in space, and where I will have the amplitude of the kick, I would have P naught and an integral on the volume. Now you see that if P naught was not vanishing, this quantity would be much larger than 1. Actually, it would even diverge with the system size. If M is larger than 1, it means that you will have an explosion, because in average, first generation, you trigger few new shear transformations. Each of them is going to trigger many new, and so on. So this cannot be the case. So in general, what you can show is that if the elastic propagator goes like 1 to the r power alpha, P of x has to vanish at least with this exponent d over alpha minus 1, when alpha is smaller than d. So those ideas are not new. I mean, they were developed initially by Efroch and Shklovsky for dirty insulators. So it's essentially following a very similar idea. Okay, so now we can think how we're going to validate those ideas. And we're going to look at elastoplastic models, essentially automaton models developed by Middleton and so on for the depinning, but applied to the yielding transition by many authors. So how do you think about, so you think again about the system mesoscopically, and you cut it into boxes, and again, the state variable in a box is the distance to the yielding transition xi. So xi is the local yield stress minus the applied stress. So the control parameter in this model is, for example, the applied stress. That essentially is it's equivalent to say that you're fixing the mean value of your xi variables. So something is, all right. Okay, so such a model captures a lot of the yielding transition. So what is the dynamical rule? If xi is smaller than 0, you must have some rearrangement. So what you do, you say that after some time tau c, the system rearranges. So the site I gets stabilized by some finite value or some random value. And the other sides get a kick, which is this propagator. Now you can play with what this propagator is. Those models, in particular, generate a yield stress. So you would have permanent flow if sigma is larger than some critical value. And to define the strain rate and to measure a flow curve, you can define the strain rate as the flux of plastic event. What is the number of plastic event sites that are relaxing per unit time, per unit volume? sorry, I don't know why my slides are coming slowly. So here in the first, what we did the first time was to play with the interaction kernel and take a kernel that's decaying like 1 over r to some alpha. And we're going to change the range of this interaction. Here we also put some random noise when we give the kicks, because the propagator is in average 0, and that's our way to satisfy this constraint. Now we play with alpha, and in the Zeus model, it's very easy to measure P of x, the distribution of the distance to the local yield stress. And what we find is that indeed P of x behave as a power law, and that this power law theta, that this is P of x for different alpha, this power law theta depends on the exponent alpha. So the larger the alpha, the smaller the theta. So that's very much related to the stability argument, so maybe I can best express it here. So that's what we do here. Alpha is interaction range, so this is very long range interaction. This is very short range interaction. I mean, power law. And here we measure systematically the exponent theta from numerics. Different colors corresponds to different system size. Our stability argument is telling us that to be stable, you have to be above this black line here. All right? So that seems to fail here, but we're confident that that's because here we have a lot of finite size effect, and you see that actually this seems to approach this line. When alpha is 0, you can do an analytic treatment of the problem, and you can prove that actually theta has to be 1. But maybe more physical situation corresponds to larger alpha. And here what we find is that it seems that the system lives in the stable region, but not too far from the marginal line, if you want. That's only suggestive because it's not too far, so I think more work needs to be done to really prove that it's not the same. But okay, so that's to show that the exponent theta actually depends on the interaction range. And then you can use what we think is a good interaction kernel. Right? So for example, we do this in 2D or in 3D. And we actually measure this P of x, and that gives us 2 non-trivial exponents that characterize the density of the shear transformation zone. We find something like O.6 in 2D and O.35 in 3D. So now you could argue that maybe we are really in our dreams and that those models are very simple and that maybe they do not connect at all to what's going on with real particles. And there is good evidence that actually our prediction is accurate. Because this exponent theta, when it's larger than 0, is directly connected to the weird finite size effect I told you about at the beginning of the talk. This is just because the amount of stress that you can increase before you trigger an instability is x mean, is the smallest distance to threshold in your entire system. So if P of x is singular, then you expect indeed that the minimal value, just from large number statistics, that the minimal value in the system is not going to scale like 1 over n. This only occurs if theta is 0, like in the pinning. But here it would scale differently. So if this is true, although it's very hard numerically to measure your P of x, you can measure x mean, because you can measure how much stress you can apply typically before you have plasticity. And that's what those authors have done in particular. So from those finite size scaling, you can extract theta. And those are the more recent data on this from Salerno and Robbins. And that compares pretty well with our elastoplastic model. Yes. All right. Okay, so in the time I have left, I would like now to use this theta exponent to propose a scaling description of the problem. And really, it's going to be a generalization of the pinning, so you can look at the review of Fisher on this, except that now theta is larger than 0. And one key result is that when theta is larger than 0, we'll argue that unlike the pinning where you just have 2 independent exponents, now you need 3 independent exponents. So let me define them. So some I told you about already. This is the singularity of the flow curve. This is the exponent that characterizes a number of excitation close to yielding. You also have a length scale, because the dynamics becomes more and more correlated as you approach the yield stress from above, defining some exponent nu. And you also have 3 exponents that characterize avalanches. So you can define a size of an avalanche S. Okay? So what you like to capture is the number of plastic events that you had. So one way to define it, for example, is to look at the drop of stress that occurred during an avalanche and multiply it by the system size. So that would be a measure of an avalanche. So there are different definitions, but so authors have looked at the distribution of the avalanches, and that characterized by some exponent tau. So that's the first exponent. Another exponent is the relationship between spatial extension and size. So small avalanches will have a smaller size. That defines an exponent df, which you can compute from finite size scaling. For example, you look at a finite volume, and you look at what are the biggest avalanches. And they should scale like this. And the last exponent characterizes the fact that if you have a big avalanche, it's going to take more time to realize itself. No, these are all numerics from... No, this? Those are numerics by people in the room. So sorry, I cited at the first slide. So I think this is Mark and Greg.
That's Craig.
This is Craig and Mark together, right? No? Craig alone? Okay.
Not for a second.
Yeah. So there is just an exponent that tells you about the duration of avalanches. Okay, so now I will go through the 3 scaling relations that connect the exponents. And the first one is maybe the simplest to understand, and it's doing some kind of bookkeeping, as was done by several authors in the field. So the bookkeeping is that if you are in stationary state, you must, in average, go up as much as you go down. So how much you go up in stress between 2 avalanches is this X mean I told you about. How much you go down has to do with the distribution of avalanches. Here in the mean, it must be equal. The mean of how much you go up must be equal to the mean that you go down. So you have to compute the mean of avalanches, and that's directly related to the distribution exponent tau and the cutoff size that depends on the system size to some power. So just equating those two, you get a first scaling relation that relate our exponent theta to tau and df. So tau, the distribution of avalanches, and df, how they grow in size with linear size. That's the first one. Then the second scaling relation, we really steal it from depinning, and it's the idea that if you're at a finite strain rate, you can think about flow as many avalanches of size psi going on in parallel. And now we can just compute what is the characteristic strain rate of an avalanche of size psi. So this is going to be the characteristic size of the avalanche divided by the volume, that gives me a strain, divided by the duration of the avalanche, this gives me a strain rate. And that gives you a second relationship between exponent, dynamical exponent. Okay, and then there is the last scaling relation, sort of hyperscaling relation. And the idea is that on the length scale psi, the stress is going to fluctuate due to those big avalanches. And you are requiring that those fluctuation of stress, delta sigma coming from avalanches, are directly proportional to the distance to threshold. Right? The fluctuation of stress on the scale psi are equal to sigma minus sigma c. So that gives you the last scaling relation. It was already pointed out by Salerno and Robin that this relation may apply in here because it applies in depinning. So what we added to that is to show that in simple model of depinning, like elastoplastic model, if you have the tilt some symmetry of the disorder, you can actually argue that it has to be correct if you assume linear elasticity. So at the end, what we get is as a summary, a scaling description where we are left with only 3 exponents standing. So we took, for example, theta, z, and df. And the other exponent can be expressed in terms of those 3 exponents. Okay, so that's a proposition. Now, maybe it's not always correct, and maybe we'll see what the future tells us. For example, does it work when you are overdamped or when you have inertia and so on? That's a question for the future. Now, what we did is to test this in this automaton model that we told you about. So both the automaton model and molecular dynamics have been studied a lot. So what we wanted to do is to have in one system to really measure all exponents at the same time. And so we measure those 6 exponents in 3D, in 2D, and in 3D. And where you can test our prediction are the 3 last exponents that we can express in the terms of the first 3. And what we find that for this simple model, the agreement seems to be excellent. There is some caveat is that when we compute tau, we find that depending on the exact protocol that we use, we can get different tau. So here we show the protocol that has the least system size dependence. But for example, if we do external dynamics, we have something that's a bit smaller, but that seems to change a lot with n. So 5 minutes, okay. But I think maybe the next talk will talk about issues like this. So I have the slides on the data if you want to see them. But here I would just conclude since it's time. Well, so maybe the key argument would be that in amorphous solid, you have to think about why they are stable at the first place. And that's constrained how much shear transformation you can have in those systems. And there is a density of excitation, if you want, and it's characterized by some exponent theta that we think is going to enter in the description of slow flow, at least at 0 temperature. Then once you have that, it's very tempting to propose this direct analogy between depinning and the yielding transition. And then the key difference with the depinning transition is that you need 3 distinct exponents instead of just 2. There's a 4th point I didn't have time to talk about, but I will just mention it, is that there's also a qualitative difference when you think about crackling. If theta is not 0, what you can argue is that in certain circumstances, you should have crackling even below the yield stress. But I won't have time to talk about this. Okay, so there are clearly things that we don't understand at all. So we propose a scaling relation, but we have no clue about, what are those exponents, what fixes their actual values. So to me, the most interesting is this exponent theta, because that's the real new things with respect to depinning. But we even don't know if it should vanish above some critical dimension where mean field should apply and hyperscaling relation should break down. I mean, even this, we don't know. Yeah, what would be the mean field description and at which dimension it would apply. And another question, which is more for the audience, is that this is for amorphous solid, but how much does it connect to plasticity in crystals, where you have dislocations that form a sort of disordered mesh? So the interaction kernel is very similar in the problem of the crystal and in the amorphous solid problem. So the same argument may apply. So do you have also in crystal plasticity those very curious finite size scaling, and should we think about the sort of density of excitation that is singular? I mean, that's more a question to the expert in the room here. Okay, so I'm done.
Okay, lots of hands. Okay. All right, so we'll start with.
Hi, beautiful talk. So I had a question about theta, and in particular, the sort of argument that you made for the prediction of theta was based on marginal stability.
Right, so exactly. So you just get a bound. Okay, so that's an important point. stability here just gives you a bound. In the problem of jamming, when we think about flow of hard particles, this bound is saturated. So it's very convenient because we can really pin what the exponent is for the distribution of forces. And we understand why it's saturated, and it has to do with the fact that interactions are not power law decaying, but infinite range, really. And in this case, with Marcus, we have an argument to really show that it has to be saturated. Here, we don't have the argument. And what's surprising and interesting, that naively would have thought that there may just be a log, that theta would be, if you want, essentially plus zero. There would just be a log vanishment of P of x, but it's not the case. So that's something we're trying to think about. Why? Okay, it has to do with spatial correlations that you have, but we don't have a good understanding at this point of why it's not saturated, why it goes beyond the bound.
So could I actually ask a question?
Yeah. I thought this was
which is that precisely like Salerno and Robbins, their system isn't marginally stable necessarily. It's close, but it's a Leonard-Jones system. So.
Right. No, but so I'm saying the same here. Here it's the same for. I mean, you were not looking at. I mean, here we're looking at some elastoplastic model. Right?
Sure. I understand all of that. So the question that I'd like to ask is...
And it's also not marginal here, right?
Yes. So the question I'd like to ask is, do you have any ideas of how you expect the sort of exponent for P of x to change, sort of depending on material preparation, sort of quench protocols, or with coordination number or pressure? Because I think that would be really exciting.
Well, so that's a very interesting question. So this theta, do you measure it? Here we measure it at the yield stress. What happens when you measure it, for example, after a quench? So how important is it for an amorphous solid, this theta? Itamar, now he says he disagrees, but from what I learned from his postdoc, Edan Lerner, and what we could check in this elastoplastic model is that if you do an infinite quench, say, of a Leonard-Jones with no shear at all, you just quench it, and you measure this P of x, you again find that it is singular with a very similar exponent. In those elastoplastic model, we could do the same. We could simulate a quench without shear. So it's isotropic, and we start with some xi positive and negative, and we let the system relax. We could find exactly, again, the same exponent theta, both under shear or after an isotropic quench. Actually, even the distribution of the first eigenvalue, the exponent theta is the same if you quench or if you shear, but the distribution of the first eigenvalue, its scaling with n is unchanged, but its distribution is changed, weirdly enough. We find exactly the same in our elastoplastic model as was found in Leonard-Jones. So it seems that it's really capturing a lot. So it seems that even after isotropic quench, it seems that amorphous solids are characterized by this exponent, that it's not trivial. Now we could ask, is it going to depend on the quench rate and things like this? And surprisingly, Edan, but that's work that he has done before joining my group, but I don't think it was published. He told me that even when he was trying to quench very slowly, he would still observe the same exponent, different prefactor, but same exponent. And that's a question for the future. Yeah.
So I think Cora next, and then Hussam.
Over here. So the theta exponent, was that the weak force exponent?
Sorry. So this theta has nothing to do with the weak force exponent. So sorry. Okay. So I talked about two problems, and I took the same notation for two things that are related physically, but are different quantities. So sorry if it confuses those who know about the jamming literature and so on. So this theta is not related to, as far as we know, is not related to jamming. So it really has to do, the one I'm talking about here, with shear transformation far away from jamming. Now, how do you go continuously? Because you can, in practice, go from the yielding transition to the jamming transition. What happens to the shear transformation, this we don't understand very well.
Okay, then let me ask about the weak force exponent then.
Okay.
So I think one of the things that's going to come up in the next talk is friction. And Lisa already mentioned protocol and attractive interactions. So do you think that
so that's okay.
Wait.
So I'm happy to discuss about this, but it's going to be a bit odd. So next week I'm giving a talk on jamming and flow and so on, where this question would be completely relevant. Here I'm not talking about granular system at all. So if there are other questions before that that are on the yielding transition. I would rather have this discussion or after if there is still time or
Okay.
or not. So it's just that it's
yeah. I'll defer.
My question is about exponent tau for the avalanche type distribution. So it is known that the mean field theory predicted 3/2. And my simulations also support such 3/2, the value of 3/2. But your argument is also based on the mean field argument, but you predict a different exponent. What is the relationship between?
Okay, so the exponent tau is not. It's a scaling. It's not assuming mean field. It's just a scaling argument, which relates tau to other.
Only dimensional counting, so that is the best.
No, that's just a scaling argument. That's in depending that would be true below the critical dimension. I mean, that's not assuming mean field. So now, in terms of the value of tau, here in our paper we cite all the literature, and so here there are many authors who actually measured this. Here I'm just citing these two authors and the sort of values that they get. I mean, there is a spread in the literature, and we report it in our paper. Then we did our measurement for elastoplastic model, and that's where we get the values I'm reporting. I guess Mark is going to also maybe shows this kind of data in his model after this. So there is a sort of spread. So I think we need more time to really.
Question there, and then.
I have a question about the way you should see the difference between the yielding transition and deepening transition regarding the theta exponent, because here you justify the theta exponent with the marginal stability argument, but I think I remember that.
Let's say stability gives you a bound, and it's not saturated, so I will not call it marginal stability for the yielding transition.
Okay, it's a stability argument regarding just the decay of the interaction.
Yeah.
And I think I remember that in your paper you use another argument regarding the fact that you have unloading zones, so the kernel has negative parts. And
right. So I mean, so that's right. So why, in some sense, why in depinning you have theta equals 0? And that has to do with the fact that the interaction is monotonic. That is, if you are a site and this is your yielding, here it's where you would start to yield. In the depinning problem, if the interaction is monotonic, what happens to you is that you're always pushed. The other sites are always pushing you toward the yielding threshold. Okay? So you have no way to forecast that you're approaching this point. And P of X cannot reflect this point in some sense. In elastoplasticity, each site is going back and forth because the kicks are random in sign. So essentially it's going to create this sort of pseudo gap in the distribution. If it was a purely diffusive process, if you have a boundary condition that tells you that the P of X has to vanish when X equals 0, you would expect to have a linear decay of P of X. And that's what we find in mean field, actually. When you are not mean field, it's not a different exponent. Yes, so there is a way to think about this exponent theta in terms of dynamics too. The fact that it has to do with the fact that sites are diffusing, and because of this diffusion, they can smell that an instability is coming. Yes.
But is there some relation between the two arguments, or between the decay or? The
what we would like to do is to have a dynamical argument that explains the value of theta, but we have not done it yet.
Let's see if we can at least get one more question we make, and let's see how quick it is. Okay, I will try to keep it quick. So there was a paper by Lemaitre and Carolee that appeared on CONMAT, which never made it past CONMAT, about 2009. And they were looking at basically like a mean field kind of setup with a propagator that did have some stabilizing regions and some destabilizing regions. And I guess this relates to Lisa's question about transients and preparation. So P of X for them started out life without singularities, and it only developed a singularity when they got up to yield. So I'm wondering how that fits in with this picture.
Okay, so we looked at their paper. So it's a very nice paper that I mentioned in my talk, actually. So indeed, what they do in this paper is a purely mean field kicks. So they look at the propagator, and at the distribution of kicks, and then they spread it everywhere in the system. And they do find some kind of gap, but they didn't really characterize. So we went to this argument again, and we are studying their model, and we think that in this case, where it's purely mean field and you don't have any correlation, it's a log gap that you have, that theta is 0 with a log. And we're developing theoretical argument for this too. Now I don't know about the system preparation stuff in their work. Yes?
It seems that I really ought to make some remark, because I know that some people in the audience will be a little bit puzzled. But you know, Matthieu, that I really like what you're doing. I think you've put this whole business together in an absolutely elegant and almost completely rigorous way. But I think everybody should understand that you're talking about a special class of systems, as indicated, if by nothing else, the fact that your responses are always size dependent for the systems, whereas a real, a metallic glass that you're doing experiments on, the response does not depend on the size of the system until you let it generate shear bands and stuff like that.
Well, I think
it's a different class of phenomena, although both phenomena involve avalanches and the kinds of things that this program and conference is.
But I would like to argue to this that it's not because we look at finite size scaling. I mean, the exponents that we can extract from finite size scaling are informative for what happens in bulk flow. So that was a bit, for example, the Hershey-Berkeley exponent at a finite strain rate, then the avalanches, we make prediction on avalanches that then would have a finite size, are not at all probing the system.
No, I mean that's just one indication of the fact that by doing this zero temperature, very small strain rate limit, you are probing a different class of phenomena.
Yeah, so I completely agree with you that there is a lot more that you could think about. There are many systems where you're close to TG, then you can have aging, you have relaxation taking place, and so on. So here I'm going away from that, and I completely agree that there's another world to explore, and you're exploring. No, but I mean, at some point those pictures have to match somehow. But that's.
So guys, I'm going to have to tell you to. I apologize to you. Okay, so
that's yours. Okay.
I'll try to get to it. Okay, so in order to more or less stay on time, thanks again to Matthieu. And so then.